anything else than just practice?
So today we are reading a story that is called The Greedy Triangle. Once there was a triangle that was, as most triangles are, always busy. The triangle spent its time holding up roofs, supporting bridges, making music in a symphony orchestra, catching the wind for sailboats, being slices of pie and halves of sandwiches, and much, much more. The triangle's favorite thing, however, was to slip into place when people put their hands on their hips. That way I always hear the latest news, it said, which I can tell my friends. The triangle's friends liked hearing the news. One day the triangle began to feel dissatisfied. I'm tired of doing the same old things, it grumbled. There must be more to life. So the triangle went to see the local shapeshifter. How may I help you? The shapeshifter asked the triangle. Well, I think if I just had one more side and one more angle, said the triangle, my life would be more interesting. Well, that's easy to do, said the shapeshifter. And poof, the shapeshifter turned the triangle into a quadrilateral. So what I'd like you to do right now is take your triangle and go ahead and make your triangle just by folding in one vertex. Your triangle is now a quadrilateral. The quadrilateral is any closed shape, therefore a polygon, with four sides. So our triangle becomes something that looks more square-ish. Yours is more trapezoidal, but that's okay. You can still count the 1, 2, 3, 4 sides. If while I'm reading, you choose to give him some sweet eyes and nose, have at it. You're welcome to decorate your triangle any way you feel obliged to. Are we good? Life changed in a wonderful way. The quadrilateral was happy with all the new things it could do. The quadrilateral could be a baseball diamond, or first, second, or third base. It could take a position on a checkerboard or a chessboard. It could be a television screen or a computer screen or a movie screen. It could frame windows, frame pictures, and much, much more. The quadrilateral's favorite thing, however, was to be the pages of a book. Oh, I learned so many interesting stories that way, it said, which I can tell my friends. The quadrilateral's friends liked hearing the stories. But one day, the quadrilateral began to feel dissatisfied. I'm tired of doing the same old things, it grumbled. There must be more to life. So the quadrilateral went back to the shapeshifter. How may I help you now? The shapeshifter asked the quadrilateral. Well, I think if I had just one more side and one more angle, said the quadrilateral, my life would be more interesting. Well, that's easy to do, said the shapeshifter. And poof, the shapeshifter turned the quadrilateral into a pentagon. You know what to do next. Take one vertex, fold it in. Now, granted, this pentagon looks a little bit different from yours, obviously, but does yours still have 1, 2, 3, 4, 5 sides? Life changed in a wonderful way. The pentagon was happy with all the new things it could do. On a baseball diamond, the pentagon could be home plate. It could be a section on a soccer ball, or appear inside whenever someone drew a 5-pointed star. The pentagon's favorite thing, however, was to be the headquarters of the United States military near Washington, D.C. Oh, I hear all the top secrets that way, it said. It's too bad I can't tell them all to my friends. The pentagon's friends couldn't help but feel left out. And in case you can't see, there's his friends feeling very left out. After a while, time seemed to pass slowly for the pentagon, and it became dissatisfied. Well, I'm tired of doing the same old things, it grumbled. There must be more to life. So the pentagon went back to the shapeshifter. So you're here again, the shapeshifter said to the pentagon. Now what would you like? Well, I think if I just had one more side and one more angle, said the pentagon, my life would be more interesting. Well, that's easy to do, said the shapeshifter, and poof, the pentagon, or the shapeshifter turns the pentagon into a hexagon. So when you fold in that last vertex, you have 1, 2, 3, 4, 5, 6 sides. And depending on how deep you made your folds, you approach whether it's supposed to be in a regular shape or not. Either one's fun. Life changed again in a wonderful way. The hexagon was happy with all the new things it could do. The hexagon fit in as floor tiles in houses and patios, fancy crackers at parties and picnics. It worked as the socket of certain bolts and the prongs of certain wrenches. The hexagon's favorite thing, however, was to be a cell in a beehive. Oh, I love watching the bees. As they buzz in and out, it said, the hexagon spent so much time in the beehive, it was too busy to talk to his friends. The friends missed the hexagon and couldn't help but feel ignored. Again and again, the shape became restless, dissatisfied, and very unhappy with its life. Again and again, it returned to the shapeshifter for more sides and more angles. The shapeshifter agreed to turn it into one shape after another. A heptagon, an octagon, a nonagon, a decagon, and on and on and on. Finally, the shape had many, many sides and many, many angles. Its sides were so small, it had trouble keeping its balance. Its friends couldn't tell which side it was on and began to avoid the shape. One day, when the shape was going down a hill, it began to roll. Faster and faster it went, screeching around corners, crashing into fences and trees, colliding with bicycles and terrifying walkers. At last, the shape came to a stop. It felt tired and dizzy and lonely and sad. Enough, thought the shape. I don't know which side is up, and I can't keep my balance. My friends don't want me around. The shape could no longer remember why it had been so unhappy as a triangle. Very carefully, it made its way back to the shapeshifter. Aren't you happy yet? The shapeshifter asked. Oh, I want to be a triangle again, said the shape. Well, I'm not surprised, said the shapeshifter. Poof! The shapeshifter turned the shape back into a triangle. The triangle was delighted to have its old shape back again and kept itself very busy. Once again, it held up roofs, supported bridges, made music at a symphony orchestra, caught the wind for sailboats, became slices of pie and halves of sandwiches, and much, much more. So the triangle's favorite thing was to slip into place when people put their hands on their hips. That way I always hear the latest news, it said, which I can tell my friends. Its friends liked hearing the news and were glad the triangle was back in shape again. Okay, so I want you to remember this picture as we move into today's lesson, because today we're going to be talking about polygons. And as we talk about polygons, we started our study of triangles, closed figure with sides. We talked about what it means to be a polygon, and we spent an incredible amount of time on triangles. Well, today we're moving into the other polygons. And I want you to think about what happens as I add a side to each shape. And we're going to talk about both interior and exterior angles. Your interior angles are going to be those inside of the shape. Your exterior ones are going to be those angles that, if we extend the side, create that angle between the side extension that are outside of the shape. But I want you to notice, as with your triangle and what we see here, each time I add a side, what shape are we approaching? Yeah. Here's an idea of calculus. It's the idea of limits. You're never going to get there. So when we talk about a circle, and that's in our next unit, circles are a shape that is a continuous line with no sides. So there's no sides, no angles to a circle. And as I get closer and closer and closer and closer to it, I can approach it, but I'm never going to get there. As long as I have a side, as long as I have an angle, I do not have a circle. So that's an interesting conversation where you think about an idea that you approach but never actually reach. There's a difference between a polygon and a circle. A circle is never a polygon. Sound okay? All right. Do me a favor, please. All right. So when we look at this, we've already had some of this content. We've already talked about what a polygon is. That's why we're going to call it review. It is a closed figure with sides. It doesn't have any curves, vertices, or any curves or vertices with more than 2 segments. So go ahead with your partner. Cross off which are not polygons. Mark and take note.
You were right.
All right. So B and E are the ones that kids always get. A is the ones that they kind of mess up on because these 2 triangles are individually polygons, but when they're together as one shape, this is not a polygon because there's greater than 2 segments meeting at each of those vertices. So for those of you in doubt, A is not.
So if it's together, it's not polygon.
True. All right, so when we talk about concave versus convex, if it's concave, figure like it dents in, like a cave. So you think about like a bear going into a cave or a cave in the side of a mountain or an ocean or a beach. If it dents in, then that's where it's concave. We can say if you can connect any 2 non-consecutive vertices outside of the shape, it's going to be concave. If you'd rather think of what it means to be convex, if a shape is convex, all of the diagonals connect inside of the shape. So whether you think about a shape being concave or convex, can any 2 vertices be connected with a segment in the exterior of the shape? If it's yes, it's concave. If it's no, then that shape is convex. So if you look at the polygons above, which one's concave, which one's convex? Go ahead. Wait, what do you think, guys?
Oh, I was gonna ask if even if there's only one concave.
Even if, yeah.
Okay.
All you need is one concave story, part, situation, then the whole shape counts as being concave. Okay?
You want us to say which ones are concave?
Yeah.
The rectangle is convex because you can't. That's concave.
No, it's convex.
Oh.
You're right.
Okay, that's convex because you can't connect like those lines that are connected.
I'll buy it.
And the one to the right, that one is going to be convex because you can't connect those sides.
Go ahead.
That one's concave because you can. That one is convex. Cave. Vex.
Yes. Convex is C, concave is D. Concave here where my arrow is, and these 2 shapes here are going to be convex. So here's an interesting conversation that we want to make sure we get right, and it's interesting, we were able to use a lot of this vocabulary with triangles for expanding beyond just 3 sides to our polygon and talking about all of the polygons that have more than 3 sides in a triangle in addition. So we could talk about whether it's equilateral, equiangular versus regular. Now, when we were talking about a triangle, our equilateral and equiangular conversations were the same. An equilateral shape was equiangular, and an equiangular shape was equilateral. Now, I have something like, Olivia called this a rectangle. What are all of the measures of the vertices, the angle measures in that shape? They're 90 degrees. Would you call that equilateral or equiangular? It's equiangular. If we look at these notations on the sides of a triangle, is it equilateral? No. So here we have an example of a shape that is equiangular and not equilateral. Here's another story for you, and we'll talk about this as we get further into the unit. This shape is called a rhombus. And a rhombus is a quadrilateral with 4 congruent sides. Is that shape equilateral? Is it equiangular? So our conversation where we talk about shapes that are equiangular and equilateral, now we need a new vocabulary word to describe one that is both. And that is when we talk about a regular shape. A regular shape is one that has all congruent sides and congruent angles. It's both. So your congruent angles is your example of your rectangle. And your congruent sides is your example of your rhombus. Everybody good with that? Thank you, Mr. Logan. All right, so here we have these names for each of these polygons. Would you do me a favor, read through, talk to your partner about which names you recognize and which are new to you. Your markers up top. All right, come back. Let's talk about some pronunciations. Triangle, you know. Quadrilateral, pentagon, hexagon. Now, depending on which textbook you read, sometimes they call a polygon with 7 sides a heptagon. Sometimes they call it a septagon. Both answers are right. So there's 2 different answers there. An octagon has 8 sides, a nonagon, 9, a decagon, 10, a dodecagon, 12. And we don't say n-gon. What do you think n represents? A number. So I heard somebody comment that skips 11. We would call it an 11-gon. Really? A shape with 11 sides is an 11-gon. How about a shape with 13 sides? How about 15? How about 152? So that n, we're going to always talk about. In fact, and this is going to happen regularly for your n represents your number of sides. And then you just add that number before the word gone, and you're set. All right, so here's a little exploration in the concept of diagonals. So what I want you to do, and I know that your space is limited, but I want you to find in this space where you can draw a triangle, quadrilateral, pentagon, or a hexagon. I want you to choose one vertex and draw all the diagonals possible from just that one point. I want you to count the number of triangles you were able to create, and then I want you to complete that table below. Thanks, Lily. Complete that table below, and I want you to try to find a pattern. Now, obviously, you can't draw an n-gon. So first of all, none of these shapes have to be regular. So just do your best to draw. So the triangle, we can all do together. And just so you're not confused, it's one triangle because I can't draw any diagonals. And the sum of the measures of the interior angles in a triangle is 180 degrees. So when we do a quadrilateral, that's a 4-sided shape. And the definition of a diagonal is a line that connects 2 non-consecutive vertices. Now, I know I can draw another diagonal here, but I'm not going to. How come?
Oh, it's kind of the same thing. Oh, true.
So you're just drawing all of the possible diagonals from one vertex. Just that one point. How many triangles do you see? Just how many triangles do you see? Okay, so that means I'm going to have, now do you understand better what I want you to do? with your partners on your mark, get set, go. All right, so let's talk about it. If I have a triangle, I have 3 sides. That's just one triangle. There's nothing fancy about that. And the sum of the interior angles is 180 degrees, and we proved that through the triangle sum theorem. So if I can remind you of like what happened then, that's when we had, remember, our parallel lines. And do you remember we had 2 transversals?
Yeah.
Do you remember that? And we talked about how these alter, or these corresponding, no. Darn it, I hate it when I do it wrong. This angle, there we go, is the same. And then we talked about how this angle is the same. And we talked about, I want pink for this. We talked about how this angle is the same. So because of the 180 degrees that exists here, pink plus green plus orange, pink plus green plus orange, 180 degrees. If you need to remind yourself of why that's true, that was how we ended up with that 180 degrees. Did you ever stop and be like, 180, who thought of that? So our triangle sum theorem backs that up. All right, with our quadrilateral, we added one more side. So when the greedy triangle went to the shapeshifter and said, I want one more side, you folded down a side, you ended up adding more angles to the interior of your shape. If you don't believe me, check it out. Look at it. Take your triangle and fold one triangle in. Take your triangle and fold one side in. These 2 angles here that you just created have a greater measurement than this one that you took away. So when you took this vertex away, you added 2 obtuse angles. You don't believe they're obtuse, just compare them to a right angle. Check it out. Here's my right angle. You know it's obtuse, right? So you added degrees to the interior of this triangle just by turning it into a quadrilateral. So the question is, how many degrees? So that one triangle means that you're adding an extra 180 degrees to the interior of that shape. Each time that pattern repeats. Here, I've added 2 triangles to my regular one, which means I've added 2 more 180 degrees. Each time I add another side, I add another triangle. I go from 1 to 2 to 3 to 4 total triangles. So I'm adding each of these numbers of degrees. So what we end up having is, if I go from 3 sides to 1 triangle, 4 sides to 2 triangles, 5 sides to 3, 6 to 4, what am I going to do from n number of sides? That number of sides, and then that n minus 2 is going to be multiplied by 180 to give me my total interior degrees. So this winds up being a formula that you need to have memorized. But in my mind, if we understand the concept behind it, you're never going to forget it. Because you can come up with your own formula just by drawing a bunch of shapes on your paper. Go ahead.
Sorry, I was writing stuff down. Where do you get the n minus 2 from?
Because if I have 6 sides, I made 4 triangles.
Oh.
If I had 5 sides, I made 3 triangles. 4 sides made 2, right? So if you look at that, each time I subtracted 2, And that's what gave me how many triangles I was able to get. Go ahead.
So it's the number of sides of whatever triangle you have.
The
and
number of
then
sides of
minus-
whatever shape.
Oh, shape. Oh, yes.
Go ahead.
Shape, and then -2, and then times 3.
Because that tells you how many triangles you can build. Each triangle is worth 180 degrees.
Okay.
Because I'm adding another triangle, I'm adding 2, I'm adding 3, I'm adding to each one of my numbers of degrees. Okay? Thumbs up if that's clear to you. All right, Abdullah gave me a good thumbs up. All right, here's the rule. You can get that easy. And like I said, we're not creative when we name things in mathematics. So somebody said, what do you want to call it? And they said, I want to call it my polygon interior angles theorem. And they're like, oh, that's a great name. I love it. So there it is. The sum of the measures of the angles, some of the measures of the interior angles, and here's something you need to make sure you remember. It's got to be convex, is going to be this equation, n minus 2 times 180. And you already proved it. And if you want to add your note, see chart on other side. Okay, so we can have this corollary, and remember the definition of a corollary is, oh yeah, while we're here talking about this, there's one more nugget that you might need to know. And the corollary says, if you have a regular agon, your regular shape, and remember, you could be like, wait a minute, I forget what it means to be regular, and you have congruent sides and congruent angles. If you have a regular shape, you can find each interior angle by dividing by n. So whether you think about it as times 1 over n or that entire thing divided by n, you can find the measure of each one if it's regular. So this next part is the part that makes kids shake their heads and be like, wait, what? Our polynomial or our polygon exterior angles theorem is the one that says, I don't care how many, I don't know why there's a line here. I don't care how many sides or angles you have. The sum of the exterior angles is always 360. You're like, how could that be true? The sum of your exterior angles is always going to be 360. And we can again go back to our shape. So take your greedy triangle, take your pencil, extend one of the sides. Acute, right, or obtuse? It's acute, right, or obtuse? It's obtuse, right? Okay? Take any four-sided shape, your paper, whatever you have, extend the side, acute, right, or obtuse?
Right.
Smaller or bigger than the obtuse?
Oh, smaller.
Smaller. All right. Now take your greedy triangle. Take your greedy triangle. Make it into a hexagon. And take a look at one of his sides. Acute, right, or obtuse? Exterior angle is? Say it out loud. Everybody. Is that smaller than the right or bigger?
Smaller.
So do you see that each time I add a side, my exterior angle gets smaller? That's because the distance around is fixed. I only have 360 degrees to divvy up. When I have 3 sides, my exterior angles are huge. When I have 4 sides, my exterior angles are smaller. When I have 6 sides, my exterior angles are smaller again. So in the picture, this is supposed to be a car that's driving around a pentagon. And notice, no matter how he drives, his exterior angles are ultimately going to add up to a 360-degree circle because he's going around. Picture him driving around in a circle. So I know that the measure of angle A plus the measure of angle B plus the measure of angle C plus the measure of angle D plus the measure of angle E, that's all going to be equal to 360 degrees because that's my circle that's going around. Same as the interior angles theorem or different? Same or different? Very different. Because each time I add a side, my total interior angles grows. Each time I add a side, my total doesn't change for my exterior. Just the size of that exterior angle gets smaller and smaller. So that's why when I say I really like this picture, I go back to this conversation because if I were to look at each of these exterior angles, if I were to extend each of these, I would see that the space between my exterior angle and that polygon side, that space between that angle measure gets smaller and smaller and smaller as I grow more and more and more angles. And this corollary, oh yeah, while we're talking about this, if I want to find each exterior angle, all I'm going to do is again divide by n, but make sure you remember it's got to be regular. All right, so we've got a couple practice problems. I'd like you to turn to your group mates, and I'd like you to work on these, have a conversation, and your mark is set, go.